Let's get this show on the road, folks. So, on 312, you guys have your next assignment due to me. Let's go over what I'm looking for. So if you go to the website and you do the how to write a lab report, okay, pretty simple thing. Tell me what you're going to tell me. Tell me what you told me. I mean, that's just the basics of writing 101. So, what are you going to tell me? Give me the big picture. What problem are you solving? And explain the scope of the work. Body of the work. Tell me. Okay? I want enough detail that I could recreate your work for verification, folks. Okay? And as always, consider your audience. Okay? If you're selling something, orient the work so that the person reading it knows what's in it for them. If you're trying to present data to colleagues, okay, think about how they're going to use that in the future and what that means to them. If you have calculations, write out the equations and define each term. Okay? Lastly, tell me what you told me. Write a conclusion. What'd you learn? You know, what'd you get out of this experiment that you did? I didn't think my lecture was that bad, certainly. Okay. So, do the following. Give me a title on all of your figures, folks. If you add a diagram, talk about it. Tell me why it's there. Okay? Never use I or me. If you're doing technical writing, the audience doesn't care about you. Okay? They care about becoming better educated. So instead of saying I or me, like I tested a pressure vessel until it failed, right? A pressure vessel was tested to failure. Okay, and it should all be past perfect tense. Everything should be done at this point, unless you're going to write about where you would go in the future because something went wrong. Okay, always in passive voice. Any data you research or use should either be cited in the body or as an endnote. Okay, don't go stealing anybody's work. Avoid slang, colloquialism, sarcasm, unsubstantiated critiques. Okay, leave all of that junk out. And yes, I have seen that in formal writing. Okay. So never write something like the U.S. economy is currently at 4% unemployment and is projected to remain there unless we have the mother of all wars. Yes, I actually saw that on a midterm paper once. Okay. The last comment is inappropriate. Leave it out. Number 6, run spell check, guys. Okay, that's really hard to imagine that I have to say that today, but yes, run spell check. Complete sentences. I can't believe I have to say that, but yes, use complete sentences. A sentence has a noun and a verb. If it does not have that, it is not a sentence. Write out numbers less than 3 words. So 40, write it out. If you got some big long decimal, okay, fine. You can write it out as digits. If an equation is a critical part of something you're testing, write it out, define the terms. And I don't want to see any cell phone pictures or handwritten formulas. Do not use imprecise values, such as the rate of inflation is 2 to 3%. Okay. If something has a defined value, use it. So instead, write something like the 100-year historical average for the rate of inflation in the U.S. is 3.22%. Okay, that's great. I can verify that. Leave subjective evaluations out of technical papers. Let the reader draw their own conclusion or guide them to a conclusion with honest data. And lastly, I can't believe I wrote this. Capitalize the first letter in a sentence. Yes, I was actually dinging people the last time I taught 443 for not capitalizing the first letter in a sentence. So please, do not lose points over that. So what am I looking for? I gave you a template. And you can literally do a save as on this. That would be perfectly fine, guys. Designing Construction, the PG 109 by John F. Kennedy. And I wrote exactly what I want. All the sections are right there. So give me an abstract. So your abstract is going to be very, very short. What you did, how you did it, what you saw, in like 3 sentences. Introduction, what are you trying to achieve, and how you went about solving the problem. Tell me what you did. And again, I should be able to recreate your work from your report. So if you have a bunch of wiring that you had to do to collect your data, cool, put a diagram in. I don't want to see any fritzing pictures. If you go to General Motors and you put in fritzing pictures in your work, you're going to get looked at like you have 3 heads. You don't want that. Okay, control algorithm. If you did something cool, tell me about it. Give me a flow chart. So again, if you have any equations like F equals MA, some obscure thing like that, okay, number of the equation, write out the terms. Finally, results. What happened? So, tell me what you learned. And then in the appendix, anything that you think supports your conclusions that you didn't really have a good other place to put it. And if you had to write any Arduino software, stuff like that, paste that in under software in the appendix. Okay? Anything fuzzy, weird, anything not gelling about that? Okay. So literally, yes?
So for software, say we use like a piece of code that you wrote, should we still put it in there?
Yes. So I've posted a whole bunch of code snippets, and you will probably have to modify them in some way. So just paste it in. Anything else, guys? Okay. So that is due on 3/12, which will be the day after class. So if you see something that, you know, you need to ask a question in class, you'll have the day after. I did post one professional report. I wrote the XH51 program report to Congress. If you want to read that, it's all about rigid helicopter rotor heads. For your reading pleasure. Okay, today, topic of the day, optoelectronics. So light plays a really major part of electronics. And let's go over how and why. We're going to start really simple. This is something a lot of you guys are probably familiar with. I think this was in your 370 controls kits. The cadmium sulfide photocell. This is a great entry-level beginner learners kind of light sensor. When it's in the dark, highly resistive. When it's in bright sun, becomes much more conductive. And these things have their issues, though. One of the problems with them is they're slow. If you're trying to send optical communications over a fiber optic network, this is not the tech you want to use. Okay. This is great for, you know, putting on top of a light pole. You want to sense whether it's daytime or nighttime, some slow-moving kind of, you know, light change. Perfect application of this. Okay, and they can be very non-uniform piece to piece. So you might have a box of these things, and they would have different calibration curves. So if you're going to use this for any kind of precision light sensing, okay, you got to calibrate each and every one. I would probably label it sensor 1, 2, and 3, and have a curve for each one. Okay, stepping it up a little bit, we got phototransistors and photodiodes. Okay, much faster, much more responsive. So if you need to do fiber optic communication or communicate over flashing lights, this is the tech you want. Or maybe you want to do something like this. Maybe you want to look at the speed of a beam break. So I went out in the barn this weekend and I made a bunch of toys for you guys, mostly you droners. So I made this nice little stand, put a load cell in it. You can put your drone motor up on the top, and then you can fire this thing off and you can measure thrust with it. And I put a phototransistor in right at the base, so when your propeller breaks the laser beam, you can actually get the speed off it. So you can get speed and thrust on this. So let's make it go. So I am going to put a piece of tape on my little laser pointer, and I'm going to shine it into the phototransistor. Help if it stayed on. So in the dark, this phototransistor has a resistance in the mega ohms, and when I put a bright light on it, it drops down to just a few ohms, so it becomes highly conductive. I'm using something called a pull-up resistor, which I will go over in a moment. And you can see on my oscope, and I'm showing 0 volts. That is conducting all of the electricity right through the ground. So now when I break the beam, you can see my voltage jumps. So if I wanted to, I could get the RPM of this motor just by watching the beam breaks using that phototransistor. Notice how nice and sharp those lines are? They're really vertical. There's a really fast turn-on time for these phototransistors. And since I'm going soft in my old age, I actually gave you guys a piece of code in the folder. So what it's doing, you can see right now I've got About 1741 RPM, something like that. If I slow it down, like 900 RPM somewhere. And this little brush motor maxes out at about 3,300 RPM. And here's what I did. So I wrote LED. I'm actually using this laser. I didn't prepare for class soon enough. I thought an LED would be bright enough. It wasn't, so I needed my laser pointer. But either way, you got a light source, the propeller's spinning, and you send it into the phototransistor. And then we time the rising voltage. In the Arduino, there's something called pull-up resistors, which are software enableable. So in the Arduino, inside the chip, there's a 5-volt power rail, and there's a bunch of 20K resistors that can be engaged by software. So if I engage that, and I have pin D2 as an input, if I take my voltmeter and I measure the voltage on that input pin, I'm going to see 5 volts, because it's just kind of hanging out. It's not tied to ground. But if I put a sensor on that, something that's going to become conductive, when I conduct down to ground, I can sense that digital input. And that is exactly what's going on over here. And I'm doing something a little bit fancy. I'm using something called interrupts. Okay? If you're not familiar with mid-level Arduino programming, an interrupt is just a microcontroller construct that says, when some particular event happens, drop whatever you're doing, Arduino, and go service this particular routine that I want you to do. In the code I've written, in the very beginning, I turn on the interrupts using this attach interrupts command, and I tell it, for interrupt 0, do this pin service routine every time you see a rising voltage on that 5-volt pin. Okay? And interrupt 0 is tied to pin 2. So I set up some serial communication and I initialize some variables. This function micros, that's the number of microseconds that the computer program has been running on the chip. Okay, it's a 32-bit number, so it only rolls over about every 70 hours. So you've got a lot of time between rollovers. I come down here, I read the potentiometer value just like you did in 370. I write to a variable called power setting. I divide the sensor value by 4, and then I send PWM out on pin 3. And that's how I was varying the speed with the potentiometer. Okay, the fun stuff happens down here, this pin ISR. So every time pin 2 sees a rising voltage, it drops everything it's doing and goes off and does this little subroutine. So it writes down the elapsed time, or excuse me, it writes down the new microsecond time. If there's no rollover, which is what's happening with this if statement, then it calculates the elapsed time since the last rising event. Does an RPM calculation, divides the RPM by 2, because there's 2 risings for every rotation. on the blades and sends that information out to the screen. So if you guys need this, know that this tachometer software is in the class notes. Okay. Interrupt, hugely powerful, but you can end up trading a very problematic debugging scenario for an easy coding solution. So use them with caution. Just for reference, that little 20K resistor, that's called a pull-up resistor. So it's pulling up pin G2 to the 5-volt rail. Just like we saw this, well, we saw the analog of this when we talked about power MOSFETs and power switching. So on the gate, we had a resistor going to ground. That's a pull-down resistor. You're hooking it to the ground rail. So again, if I want to create a signal, I can just tie that D2 to ground, and that's exactly what the phototransistor is doing over there. Okay, so if you want to turn on these input pull-ups and make a very, very clean input phase, here's the command you use. Okay, so that's phototransistors, folks. Very nice for fast switching when you're trying to look for things like beam breaks or you want to transfer data optically, stuff like that. Another common device that we use a lot in optoelectronics is this idea of a photo interrupter. So with this little thing, you've got an LED on one side, you've got a phototransistor on the other. And if something opaque passes between the gates, it sends a high or low signal. We use these all over the place at DuPont Medical for robotic end-of-travel devices. Really nice. As long as it's a clean environment, those things work great. All right, so in the previous lectures, we went over things like looking at the load cells. Okay, the signals are really, really small, and we have to amp them up to something that's a little more, a little easier to work with. The problem with those tiny signals is they're really easy to corrupt. If you run something like power cables in the same hole as a data signal or a measurement signal, your machine can absolutely freak out on you from induction. Okay, so always, always, always run data stuff away from power cables. And one of the other problems, you want to isolate control side of your control system from your power handling side. The reason is that thing I told you about with power MOSFETs called the Miller capacitance. So the Miller capacitance will actually link your power section and your control section. That's a bad thing. Because if you get into something oscillatory with high voltages like this, okay, this is the coil pack off my GTO. This puts out about 40,000 volts. And it's an oscillating AC signal that goes to the spark plugs. You do not want this signal going back to your 5-volt Arduino. This would be bad. So the way we get around that, when you've got some, big switching, big current, big induction that can talk back through the gate of your transistor, is this little job. The opto-isolator. All this thing does, it's got an LED right here, it's got a phototransistor in here, it's all built into the case, and when you want to send a data signal to turn on your power, you light up the LED side, right there. and an infrared light beam goes over to that phototransistor, makes that conductive, and fires off your power side. Okay, the nice thing about that, guys, the data can only go one way. There's nothing connecting your control logic to your power except a light beam. And there is no way for that phototransistor to send something back and affect your controller. And this is actually how you would implement it. So if I have a 5-volt source and I've got a 500 ohm current limiting resistor, that will light up the LED, and then my 12-volt battery will start flowing current, and I can light up the little bulb. Okay, obviously things can get a whole lot more complicated than that, but these things are really just that simple to operate. Now generally on the power side, we're probably sending pins 4 and 5 up there. That's probably going to drive some big power MOSFET. It's going to move some huge amount of amperage. Okay. But for this example, that works. The nice thing about this, you have isolation up to about 5,000 volts. So if the secondary coil reflects, a few hundred volts back into the primary of this thing, but it's optically isolated, don't care. It's all good. And my favorite statement as a student when I was in your chairs was always, great, well, where am I ever going to use this? Okay, this is a stepper motor driver. And I like this example because it actually shows you, you've got a bunch of photo diode symbols up there, and you've got like pulse positive, pulse negative. Okay, that actually shows you that is an optically isolated control system. So you're going to fire off your control stuff in the signal block up there, but your high voltage motor control stuff, that's all coming out the bottom. This is how we do it actually in the real industrial world. So there are 2 isolated grounds to this. You can have your high voltage ground on the bottom, and that is utterly independent of what you're doing on the top for your control signals. A lot of times if I'm doing an Arduino stepper motor project, what I'll do is I'll have all of my power stuff going on in the bottom, and then I take like pulse negative, direction negative, enable negative, daisy chain all those together, send those to the Arduino ground, and I'm good. I don't have to worry about anything coming back at me. Because whenever you switch a coil, remember, if I've got a very high DIDT, well, that screams out I'm going to have a really high DVDT. So when that coil's magnetic field collapses, it comes rushing in on those copper coils, your voltage goes to the moon. Okay, but we can take this even a step further. We can have even more fun. Imagine that I have an LED and I have a solar panel, photovoltaic solar panel. I can actually create a completely, utterly independent source of voltage. Now that's fun. That will let me go turn on a MOSFET just with the output of this thing. And I still have all that nice optical isolation. So again, this is more like what you would really do. So we have our control side over here, our 5-volt stuff going on. And maybe we're going to use this PVI 5080N, and we're going to drive the gate of this P-channel transistor. Actually, that's an N-channel, sorry. So we're going to use that MOSFET right there. That's going to do our heavy-duty power switching. Now our bulb could be, 24-volt headlight out of a trailer truck, something like that. So these are very nice. It's an independent source. Where these get to be good is when you start getting into bridges. We're going to talk about those when we get to motors. How you make a DC motor go forward and backward. Okay, you're going to end up with 4 transistors in a bridge configuration. And the problem is your high side can get really tricky to switch on because you got your back EMF working against you at high speeds. This gets around all of that. Downside of these things, they're a little bit slow. Okay, you've got an LED, you've got a solar cell. Not a lot of power. And you still have to charge up that gate capacitance. It takes time. But this can be an independent source of either 5 or 10 volts. So that's quite nice. All right. Damn. I finished too early. Questions? Opto's great, but it is short.
What was the system that you were showing? Did you apply that to any of the everything?
Yes. Yep. Anything that can be an input, you cannot use that on the analog ends, but any of the digitals, absolutely.
Is there a way you can actually get that data off of the Arduino and like put it into an Excel file or something?
Yes, and that's what the Crosby machine controller is all about.
Okay.
So go back and watch the video for lesson 2, I think,
Okay.
where I actually did that. I took the potentiometer, I throttled it to create some analog inputs,
Okay.
and then I logged that with the Crosby machine controller and pulled it into Excel.
Okay.
Yeah, I would strongly advise you guys, if you're going to use the Crosby machine controller for data logging, get on it. You don't want to wait till the last minute. You guys aren't trained in Visual Studio, so if you have any issues, just come see me, but do it early. You don't want to be jammed up at the end.
For those little, like, EV devices, what strength of signal can you get out of that? If it is just a solar panel lighting up off an LED, it's gotta be pretty weak, right?
It's very weak. Yeah, but if all you're trying to do is light up the gate of a MOSFET that's in the picofarads, it might take a millisecond to charge the gate on that MOSFET. In electrical terms, that's an eternity. For us mechies, a millisecond is pretty darn fast. But yeah, you can get an independent 5 or 10 out of it.
Are there isolation circuits that go from the motor to the controller? Because you might want to stable the motor from the controller's perspective. Basically, you communicate from the controller to the motor and from the motor to the controller.
Sure. So you could have circuitry in the motor that sends stuff back. And in fact, our next get-together, I'm going to do encoders. So we'll go through, how do you track rotation, which would answer the question of where is my motor, what's going on with my motor. And you could certainly look at things like, what's my motor current, that kind of stuff. Anything else, folks? Yes.
What year is your GTO?
05. Yeah, I thought about, getting one of the old cool ones. But there's something nice about being able to sit in traffic with the air conditioner running, making 400 horsepower with parts readily available off any Camaro, and still get 25 miles a gallon at 100 miles an hour.
No, those are the sleepers, early 2000 GTOs when they brought them back.
What's that?
Those early 2000 GTOs when they brought them back are wicked sleepers, yeah.
Yeah, they are. So, for those of you that are wondering what in the world we're talking about, So that's mine, but in silver. So let me tell you something, guys. Someday when I'm an old feeble man and I go to get in my little grocery getter and I've got my cane and I jump in, you know, like my 2037 Corvette ZR1 with 2,000 horsepower and twin turbo and a blower. If the doors fall off, I'm coming after your degrees.